Let's look at another sample problem. This one involves friction. What we have here is a wall, vertical wall and a horizontal floor. There is a little bit of friction here. There's no friction there for simplicity. There's no friction there. There is a friction at contact point at the lower end of the ladder. Okay, point A. You know, without friction, the ladder is simply going to slip. It will never stick. Okay, but with friction, it is possible for the ladder to stay put. But you know, this angle theta cannot be too small. Okay, if the ladder is like that, very much near horizontal, the angle theta is very small, chances are it's going to slip. If I know all the necessary information, I know the length, I know that the ladder is uniform with a total mass m, okay, so the weight is mg, and also know the coefficient of static friction between the ladder and the floor. What I want to know is, what is the minimum angle theta such that the ladder can still stay put, it will not slide down? Okay, what is the minimum value of the angle? So the angle is any smaller than that, it's going to slide by itself. That is the question I want to know. Okay, we begin by identifying all the forces on the ladder. This mg, there's another force, there is a normal force here, right? Let's call it N2. It's normal to the surface of the wall. There is no friction here, so there is no force along the wall. And at the contact point, there are actually two forces. One is N1. What's that? Well, that's the normal force, right? But in addition to that, there is also a friction. The question is, what is that direction? What is the direction of that friction? Well, you know, the static friction is against the tendency of motion. What's the tendency? The tendency is for the ladder to slide this way, okay? Slide this way. So friction being against that must be that way, all right? So we conclude that the static friction must point this way, Fs. Okay, so my question is, what's the minimum value of the angle? You notice when the angle is at minimum value, this thing is on the verge of sliding. Okay, it is just about to begin sliding. When does that happen? That happens when static friction has already reached its maximum possible value, and that is Fs equals Fs maximum. That is the critical moment when it's just about to slide. And what is that equal to? That will be equal to mu s times the normal force, which is N1. Okay, so if the static friction equals this value, then we know it is just about to slide. So we have four forces, N1, N2, mg, and Fs, which is equal to this, by the way. We're looking for this angle theta. How do we proceed now? Well, we can apply the torque theorem about any point, point A, point B, or whatever other point, and I can also apply the net force equal to 0. How many unknown forces do I have? Well, I don't know what N1 is. I don't know what N2 is. Right? Is there a way we can find an equation which at least eliminates one of them, N1 and N2? I don't know how to eliminate both of them from the same equation, but is there an equation in which N1 doesn't appear or N2 doesn't appear? Well, the answer is yes. If you apply torque theorem to here about N2, about point B, then N2 does not appear because there's no lever arm. And you apply torque theorem to point A, then N1 does not appear, plus Fs does not appear either. Okay, because Fs also passes through that point. That way, if I apply the torque theorem to point A, I don't have to worry about N1 and Fs. I will find an equation in which there is only one unknown, and that is N2. Now, that will give me N2. So you say, what happens when I get N2? Well, once you get N2, remember, our job is to make sure that Fs equals this value. Okay, Fs equals this value. Then N2 is a horizontal force pointing to the right, left. It must cancel with Fs pointing to the left because net force horizontally has to be equal to 0. So that will give you a value for Fs. From Fs, because Fs is equal to this, then I know what N1 should be. But wait a minute, N1 is equal to mg, right? Because you only have one force going up, one force going down. And then we can find the result. You see? Okay, this is not the only way to do it, but it's certainly one of the better ways to do it because we can start with an equation that gives us directly what N2 is. Okay, so let's do that. Apply torque theorem about point A. Okay, about point A. The length of the rod of the ladder is L. What is the torque provided by mg? Well, it's torque at point A. Okay, mg has a torque of mg times what? Lever arm. Okay, this is the line of action. The lever arm is from here to there. It's from here to the line of action. In this right angle triangle here, this is the lever arm. Okay, and you have L over 2 cosine theta. Right? L over 2 cosine theta. That is the lever arm from here to there. That is a clockwise torque. It must cancel with the counterclockwise torque provided by N2. So minus the counterclockwise torque provided by M2. That's N2 times what? Lever arm. Again, from point A, you drop a perpendicular until you meet the line of action. This is the line of action of N2. So you go all the way from here to there, and that's essentially this length. What's that? That's L times sine theta, right? L sine theta. Okay, L sine theta. And that has to equal to 0. That immediately tells you what N2 is. Okay, so N2 equals what? Equals mg over 2. There's a cosine theta, there's a sine theta, so it's divided by tangent theta. Right? That's N2. N2 goes this way. It must cancel with N1 going that way because these are the two only horizontal forces. And that must be equal to Fs, which must in turn be equal to mu s times N1. Right? So that tells you what N1 is now. N1 simply is just N2 over mu s. This is N2 right here. So I have N1 equals to mg over 2 mu s tangent theta. Okay, that is what N1 has to equal to. But wait a second, as we know, N1 must cancel with mg because these are the only two vertical forces. They must add up to 0. So that equals mg. Right? And mg and mg cancels out nicely. To make this work, you find that the angle theta which satisfies this equation must satisfy 2 mu s tangent theta equal to 1. See that? Okay, because this has to equal to 1, mg cancels. So tangent theta must equal to 1 over 2 mu s. So for example, if mu s equal to 1, okay, see if this ladder has a rubber end, then rubber and this dry concrete, rubber on dry concrete, mu s equals 1. Okay, so tangent theta will be 1/2. That tells you what the angle theta is. And this formula is also, you can look at some special cases. If mu s is very, very small, okay, it's very, very small, so that means the road is very slippery here, the floor is very slippery here, then this value 1 over 2 mu s is very large, which means the angle tangent theta, the angle theta has to be very large. In other words, the ladder has to be almost vertical to prevent it from sliding. And if mu s is very, very small, very, very large, then tangent theta can be very small. You can put the ladder almost like this, it still will not slide. That makes sense. Okay, in particular, when mu s equals 0, that's a completely frictionless floor. There's no way it will stay at rest as long as theta is not equal to 90 degrees. The only way to stay put is when put theta equal to 0, equal to 90 degrees, so it means the ladder is just leaning against the wall like this. That happens when theta equals 90 degrees or tangent theta equals to infinity. That happens when mu s equals 0. So that makes sense. Okay, it satisfies this special case. So again, that is an example in which we utilize both the net force equal to 0 and net torque equal to 0, along with the critical condition when this thing is just about to slide, Fs equals to its maximum value. Finally, we look at this amazing example. A stack of n books, each is like a little, for simplicity, like a brick of length L uniform. Okay, what I want to do is I'm going to take one book first. I'm going to put against on the edge of a table so that I move the book halfway in, halfway out. The book is on the verge of sliding off the table. Okay, so the center of gravity of the book is right at the edge. So the edge of the table gives it a supporting force right up, right here. And its own weight is right down, so it cancels out. See, if the center of gravity is a little bit over the edge of the table, it's going to tumble, of course, it's going to fall. So n equal to 1, n is the number of books. When n equals 1, the edge of the book has to be halfway in, halfway out. Okay, it's like this. So the overhang, this distance from here to there, it's called overhang, is L over 2. And that's trivial. Now, what I want to know is what happens when you got two books. How do we stack them up so that I get the greatest overhang possible? So I get two books like this. Okay, this time I have to be a little bit more careful here. Here is one book, and here is another book. Now, if you think of both books as the same system, then the combined center of mass, okay, of both books must be right at the edge if you want to go all the way as far as possible. Because if the combined center of mass is over that edge, it's going to fall. Okay, it's going to fall for sure. So, how do you find the combined center of mass? Suppose, first of all, the books are just aligned so that this end and that end are aligned. You slide this book a certain distance, and slide that book another distance. The center of mass remains here. Okay, remains right in the middle. So the question is, how far can you slide this book this way and that book that way? Okay, to answer this question, we have to look at the first book to make sure the first book alone also achieves a balance, not just both books. The first book alone has to achieve a balance. And that's just like that situation, right? The second book now acts as if it were the edge of a table. For the first book to maintain equilibrium, you want to make sure that this supporting point is at the center of mass of the first book. Okay, so as far as the first book is concerned, it can go no further, this overhang is no further than L over 2, just like that. Okay. Then the question is, how far should I slide the second book? Well, the idea is the combined center of mass remains here. As the first book goes forward, the second book goes backwards. That creates this gap, right? This gap total is L over 2. But this book going forward, that book going backward, they have to go by the same amount in order to make sure the center of mass of combined book, the two books, stays right at the edge. That means this book has to go L over 4, that book has to go L over 4, so that totally I get L over 2 here. Alright, so how far should I slide the second book back from the edge of the table? That's L over 4. So basically I take those books like this, right? I slide this guy L over 4, slide the first one forward by L over 4. I create an overhang of L over 2, and I create another one of L over 4. Okay, so what's the total overhang this time? It's L over 4 plus L over 2. That's 3L over 4. Okay, so I'm getting a little bit further out with two books. Okay, now let's look at the case with three books. What's the total overhang? Now, first of all, the top two books, just like that, okay, the combined center of mass is here for the first two books. It's here, and it is a distance L over 4. A distance L over 4 from the edge of the second book is right here. Okay. What I want to know is the overhang of the third book, which I call x. What is x equal to? Well, you see, I can divide this thing into two parts. The first part consists of the first two books. The second part consists of the third book. The combined center of mass of the three-book system must be right here so that you can have a supporting force at the edge of the table. Let's call this x. Okay, so for the first two books, the combined center of mass is a distance x out, right? Because it's right here. There's a distance x out. So it's 2 mg. That's the total mass of the first two, total weight of the first two books times x. Okay, the third book has a center of mass right here. Now remember that distance is L over 2, but it sticks out a distance L. X. Therefore, relative to this point, this distance will be L over 2 minus x. Okay, so it's L over 2 minus x times its weight mg. Okay, that will be a formula for x because that 2mgx really is the torque provided by the weight of the first two books going this way about this point. That term is the weight of the torque of the weight provided by the third book going that way. These two torques should cancel about this pivot point right here. And that easily gives you x equals 6 over L. So the overhang is L over 6. Now, I hope you can see a trend here. For the first book, the overhang is L over 2. Second book, the overhang is L over 4. The third book, the overhang is L over 6. And what if I have fourth book and fifth book? Well, it goes from 2 to 4 to 6 to 8 to 10 and so on, right? All right, so here's the amazing thing. Suppose I have a stack of n books, 1, 2, 3, 4, 5, and so on. I stack them out like this. You get L over 2, L over 4, L over 6, L over 8, and so on. I want to know what's the total overhang. Now, isn't that equal to L over 2 plus L over 4 plus 6, 8, and so on? Suppose I have a whole bunch of books. Okay. Suppose n equals infinity. I have a whole bunch of books. What does that lead to? You know 1 plus 2 plus 1 over 4 plus 1 over 6 plus 1 over 8. That's an infinite series, and that series does not even converge. It approaches infinity. Now, what does that tell us? It tells us counterintuitively that as long as you have enough books, the overhang can be as far out as you want. It can go far out from the edge of the table. It can go all the way to the moon if you really wanted to. If you have enough books, that is, assuming the gravity never changes. Okay, now that is an amazing thing because we didn't expect, really. We didn't even expect the overhang, total overhang to be greater than L, because that way the first book is totally out of the edge of the table. In reality, that can happen, definitely. And you don't need an infinite number of books to achieve that. Infinite number of books will get you to infinity, okay? How many is the minimum number of books necessary so that the first book goes out from the edge of the table by more than its own length? Well, you have to add 2, 4, 6, 8 until you stop at a number where the total number is greater than L, and that happens with as little as 4 books. 1 plus 2 plus 1 plus 1 over 4 plus 1 over 6 plus 1 over 8 is equal to 1.04. It's greater than L. So with only 1, 2, 3, 4, 4 books, the edge is already over 1L away. That is already amazing. We can do this demonstration and see it for ourselves.